Good morning, all of you. So today we would be start the lecture with a new topic, that is low dropout regulator. In the previous lectures, we have seen the LM371 voltage regulator, adjustable voltage regulator, LM337, and how can we modify that particular circuitry to boost up the output current. That much amount of discussion we have already done in this particular unit. Today we would be discuss uh, one of the problem occurred in the regulator, that is dropout, voltage dropout. So to overcome that, there is a another voltage regulator, that is low dropout voltage regulators are available. First of all, we have to be discuss this problem. Now, if you would be see voltage regulators are generally used to provide a stable power supply, and that stable power supply voltage would be independent of load impedance, input and output voltage variations, temperature, and time. So your output regulated voltage should be independent of this much of the factors. Low dropout voltage regulators are distinguished by their ability to maintain the regulation with small differences between the supply voltage and the load voltage. And the difference between unregulated input voltage and regulated output voltage is called dropout voltage. So whatever the difference would be there in between the unregulated voltage, input voltage, and output voltage, that is considered as a dropout voltage of the regulator. And actually this difference should not be there, but if such kind of the difference of the voltage would be at the output voltage, then means there is some problem, and this is the problem of the voltage dropout. So dropout voltage is the minimum voltage difference between input and output terminals that needed to regulate the supply voltage within the specification. It is a minimum voltage difference between input and output. So if you would be see some examples, like if you have to be consider the linear voltage regulator like 7805, it needs 2.5 volt maximum dropout voltage. This indicates that minimum unregulated input voltage must never be less than, the equation is mentioned here, V reference plus dropout voltage. That is, in the case of 7805, reference voltage is 5 volt and dropout voltage is 2.5, means it would be 7.5 volt. So if you want to obtain the fixed 5 volt regulated voltage at the output terminal of the 7805, so at that time at least minimum you have to be apply 7.5 volt to the input terminal of the 7805. or maybe more than at 7.5, but it should not be less than this. Otherwise, it would be not able to generate the regulated voltage of 5 volts. Okay, so there would be some performance problem. So similarly to 7805, the disadvantage of the LM317 voltage regulator is that it would be also need at least 3 volt dropout voltage. It would be need at least 3 volt between its input and output in order to provide the power to the internal circuit. So in the case of 7805, it having the dropout voltage 2.5 volt. In the case of LM317 that we are actually learning in this unit, it would be also having the problem of 3 volt of dropout voltage between the input and output terminal. So through this particular diagram, I have just tried to explain what is the dropout voltage. You can see in this particular diagram, this is LM317 having the 3 terminals. This is the input terminal, and second one is output, and third one is the regulator terminal, reference terminal. So in between input and output, how much the difference of the voltage is there? This is a 3 volt. This is nothing but your dropout voltage. So here, if I want to obtain suppose 10 volt output, so I would be required here 13 volt minimum. Even the LM317 having the wide range 2 volt to 35 volt, but suppose you are going to design a regulator or power supply that should be at least 10 volt as output regulated voltage, then you have to be minimum 13 voltage required at the input side. Okay, so this is the problem of the dropout. So higher the dropout is the problem, because it would be increase the power dissipation in the IC. So our objective is here to reduce the dropout voltage. This is our main objective, because higher dropout would be create a problem of higher power dissipation, and that would be responsible for damaging of the IC. Hence, in typical application that involves the batteries whose voltage can easily drop from 12 volt to 6 volt. In such cases, like a car battery, you can see that is having the 12 volt, but it could be dropped up to the low as 6 volt because of this dropout problem. And it would be happen in such kind of the application, that would be a detrimental factor or damaging factor for that particular battery. So we have to be deal with here with LDO regulator, that is ideal solution to overcome the dropout problems. So here you can see here, this is a diagram of the LDO. You can see in the basic block diagram of this particular LM317, we have do some modifications, and here you can see we have used the 2 PNP transistors. So all of you please note it down, this particular diagram. You can see the structure of this circuit diagram is similar to the internal circuit diagram of the LM317. Only the difference, we have connected 2 PNP transistors, Q1 and Q2. This is your comparator, you can say. In the inverting terminal, it is connected to the V reference voltage that is coming out from this Zener diode. Then we have applied the input voltage on this same particular inverting terminal, and non-inverting terminal is connected to the middle of the R1 and R2, and R1 and R2 are the resistors connected at the output network. So you can consider that your inverting terminal, non-inverting terminal is acting as a feedback. It would be construct a feedback loop. So we would be see the detail operation. First of all, please all of you note it down, and we have to also see that what are the rows of this Q1 and Q2 here. Okay, so I hope all of you have noted down. So this V in is same here, and you can consider the cut-in voltage of this part. This Q1 is nothing but it would be acting as a series pass element or series pass transistor to drive the output. To driving this output, this Q1 would be act a role of series pass transistor. So the cut-in, you can say it is a PNP transistor. This is your emitter E1, this is collector, and this is base. Similarly, for this Q2, this is base, this is your E2 and C2. Now, you can see I have said that Q1 is acting as a series pass transistor to drive the output voltage. So you can consider here the cut-in voltage. So what is the cut-in voltage here? Either you can consider it a 0.6 or 0.7 volt. For it is made up from the silicon. Similarly, here also for the Q2, 0.6 volt we have considered. So the total voltage at this error amplifier output is Vi minus 1.2. The addition of this, you can apply the KVL on this loop. So Vi minus 0.6 minus 0.6 is equal to 0, means Vi minus 1.2. This is the output of this particular error amplifier, you can say, or you can say buffer output. Okay, and this Q2, the transistor Q2, PNP transistor Q2 would be act as a buffer here between this error amplifier or op-amp and Q1. Why it is called as a buffer? Because Q2 would be provide the base current to the Q1 without loading the op-amp. So I hope all of you have drawn this. Now we have to see the analysis of that. So here we have see that we have employed the PNP BJT as a series element to drive the output. Q2 would be act as a buffer and it would be maintain the output of an output at this Vi minus 1.2 volt, and the non-inverting terminal is voltage at the junction of R1 and R2 is fed back to the non-inverting output of the error amplifier. If you would be seeing this particular diagram, same thing is okay. Now, when this voltage, which voltage? The voltage that is coming out from the junction of R1 and R2 towards the non-inverting terminal of the op-amp. When this feedback voltage, you can say, it is more than the reference voltage that is set by the Zener diode, and that is applied to the inverting terminal. So when the voltage at the non-inverting terminal is more than that of the reference voltage applied at the inverting terminal, the op-amp or the output of the op-amp would be goes to positive. Its output would become positive, and this positive output would be reduce the base current of Q2. It would be reduce the base current of Q2, and because of that, which in turn what happens? It would be reduces the base current of Q1, because Q2 would be act as a buffer for the Q1, and as the base current of Q2 would be decreased, the base current of series element Q1 would be also decreased. Thus, Circuit realizes the minimum voltage of 0.2 volt nearby, that is being nothing but the voltage between the emitter and collector terminal of the Q1, or you can say it is the voltage difference between the input and output terminals, because emitter of Q1 is connected to the Vi and collector is connected to the V0. So because of this process, what you have seen, there is a minimum voltage difference between the Vi and V0 that would be reduced to the 0.2 volt. That was in the past 3 volt in the case of LM317, but when you would be do some modification and make the LM317 as a LDO, low dropout voltage regulator, so it would be offer only 0.2 volt as a voltage difference between the input and output terminal. That is the change occurred because of this connection. So you have to be just noted down that transistor based drive from op-amp is relative to the input voltage. Instead of that, you can use the IC LM2941. It is also a typical low dropout positive voltage regulator that is available in the market, and it can source up to the output current of 1 ampere with typical dropout of 0.5 volt and a maximum of 1 volt over the entire temperature range. Okay. So these are the description about the low dropout voltage. I would also just explain the mathematical equations that would be give you the better idea that how this voltage would be drop out to the lower level from this based on this particular circuit diagram. So if you would be refer this circuit diagram, so yeah, I have to just mention certain points in this particular circuit diagram, like this is your already we have seen 0.6 volt, 0.6 volt, it is your Vi. Okay, this is your Q1 and Q2. You can consider this is as a Vf or V reference. Okay, that is similar to that at the initial condition. We would be see where it would be increased more than this. And apart from this, the output of this op-amp would be considered as a VA. VA is nothing but Vi minus 1.2. How this would become? It is easy to find out. Suppose what we have see that the Q2 provide a base current are acting as a buffer for the Q1 without loading the op-amp. So here, if you were to apply the KVL in this particular loop, so you would be find that V in, that is Vi minus VEB1 minus VEB2, emitter to base voltage, emitter to base voltage up to Q2, that is equal to the VA. That is your equation 1. And assume that both transistors are working in active region. Okay, so hence what happens, VEB1 it is equal to VEB2 it is equal to 0.6 volt. So it is Vi minus 0.6 minus 0.6 it is equal to Va. So what is Va? That is output of the op-amp. That is Vi minus 1.2 volt. This is your equation number 2. Okay. So in this way I have got that particular value of VE minus 1.2. Now you can see the inverting terminal having the voltage. What is the voltage of inverting terminal? This inverting terminal having the voltage of V reference. Okay, that is coming out from the output of the Zener diode. And we know that in the op-amp we use the concept of the virtual short circuit. So if according to virtual short concept, what happens if the inverting terminal having the voltage of V reference, so we would be consider this particular in non-inverting terminal would be also the same voltage as V reference. That's why it is written here as a V reference here. Okay. So in this condition, it would be C. So what would be the value of the voltage at the output terminal of this particular LDO? It would be C. So the output voltage across this particular point or R2. So what is the voltage across this R2? What is the voltage across this R2? If you refer according to voltage divider rule, so it would be written as the voltage across R2 is equal to V reference as from the virtual short concept. So V reference is equal to what? It is R2 upon R1 plus R2 into V out, that is output voltage. If you see that this particular network, V output is the maximum voltage, so it would be divided into two parts between R1 and R2. Okay. So from this particular equation, we can define the formula of V out. So V out is equal to what? R1 plus R2 upon R2 into V reference. So it is what? R2 R2 1 cancel 1 and R1 upon R2, it is equal to V reference. V out become a function of V reference. Depending upon the value of the R1 and R2, it would be change its value of the V out. So if the V reference is what? V reference is nothing but the voltage at the junction. So Vf is equal to V reference here. You can see on this particular diagram. So if this Vf would be, this is given to in this particular in non-inverting terminal, it is higher than this value of the V reference, because the value of Vf would be depend upon the formula we have written. V out is equal to 1 plus R1 upon R2 into V reference. If this value would be like that, we can consider this is more than the value of the V reference. At that moment, what happens? The op-amp output VA would be become more positive, and it would be become more positive, the base current of this Q2 would be decreased, and if the base current of Q2 would be reduces, the base current of the Q1 would be also reduced, and if the base current of Q1 would be reduced, that means what happens? The output voltage V0 is reduced. So in this way, the voltage difference between the input and output voltage would be reduced, and our objective would be fulfilled to decrease the difference, dropout voltage between the input and output terminal. All of you understood? Anyone has any doubt regarding this circuit explanation? You can ask me. Shubham? Bharitkar Shubham? Clear? Or any question?
Okay.
Yes?
Okay. No, sir.
Your audio is not clear.
No, sir.
Okay. Anyone else? Those want to ask any question? Otherwise, we would be move to the next topic. So there are some selection criteria of LDO, that is input voltage range, output voltage, or either it is a fixed regulator or the adjustable. I have given the example of both. 7805 is the fixed regulator, adjustable is LM317. Or output accuracy over line, load, and temperature. Low current requirement, dropout voltage, power supply rejection ratio, output noise, quiescent current, and shutdown current. So these are the 9 factors on which the selection of a LDO would be depends. And this is very important element or for the application of battery charging or mobile charging, or you can say that the car battery charging, like this. In this kind of application, the role of LDO is very important. Okay. So the next topic is switch mode power supply, SMPS. But I would be explain this topic in the next lecture. Today there is some questions asked by your classmates to me in the WhatsApp regarding the solution of the assignment number 2, second question. So I am here with one of the similar kind of example that I have given you as assignment in the assignment 2, question number 2. So if you would be see this particular question, only the parameter is different and rest of the elements are same. And see the question, and whatever the solution I will be told you today, on the basis that you have to be solve your assignment. Okay, so you can see this is the question based on the voltage series feedback amplifier. So you can see here, this is a MOSFET. Its gate is having the input voltage. Input terminal is connected to the gate terminal of the MOSFET. Its drain terminal is given to the fixed voltage of the supply VDD, and output is taking out from the source. And through the source and the ground, in between the source and ground, there is a resistor RS is connected. And I have also mentioned in the circuit diagram, between the RS, we have to be calculate the feedback voltage VFB. That means what? RS is a feedback element. And if you would be consider this circuit, if you remember the configuration that you have learned in the unit number 1, this configuration is very much similar to the configuration of source follower circuit. It is nothing but a source follower circuit or common drain circuit. It is a common drain circuit. So common drain is also considered as a voltage series feedback amplifier. I have given you a very simple example of single stage voltage series feedback. There is also the 2-stage voltage series feedback also. Now solve this numerical. The given parameters are RS is equal to 1.5 kilo ohm, threshold voltage is 1.2 volt, lambda is 0. Assume the transistor is biased at IDQ is equal to 1.2 milliampere. If transistor conduction parameter Kan is equal to 1.5 milliampere per volt square, you have to be find out AVF, means voltage gain with feedback, that is V0 upon V in. V0 is measured across RS and V is the input voltage. So whatever the ratio, that is nothing but the voltage gain with feedback, because output is connected across the RS. So it is already a feedback voltage. Sorry, voltage gain with feedback. So whatever the voltage gain of the common drain circuit or source power circuit here is the same as the voltage series feedback gain. And what is the R0F? It is the output resistance with feedback. So start to solve this numerical. You can solve this numerical by the two way. So first and straight for a simple way I have to be just going to told here. Solution is this. We know that lambda is given, means we have to find out the finite output resistance of MOSFET 1 upon lambda ID. Lambda is 0, means it is infinite. So it would be out of the consideration during our mathematical analysis. It is it made the numerical simple. Now we have to find out GM, transconductance. So what is the formula as per given parameter? There is a two formula we have learned. One is the twice of Kn Vgs minus Vth, and second one is this twice of root under Kn into Id. So what would be the value? Kn is 1.5 milliampere per volt square into Id is what? 1.2 milliampere. So you have to be just take a product of this 1.8, that means unit is milliampere per volt. So it would be came when you have to be solve this 1.3416, nearly 2.68 milliampere per volt. Okay. Now, as per the general formula of voltage gain of any amplifier, what we done? GM output resistance, but generally it is RD parallel, but it is now infinity, so it is GM RS only, and it is a positive because it is a common drain circuit. Output is positive here. There is no phase shift. So what is there? 2.68 milliampere per volt into 1.5 kilo ohm. So it would be, take a product, so it would be coming nearly 4.02. AB is unitless. Now we have to find out the beta. What is beta? This is Vf upon V0. So see in the circuitry, here Vf and V0 both are same, because V0 is across the voltage of Rs, and Vf is also the same thing, voltage drop across the Rs. So beta is equal to what? It is 1. Now calculate the D sensitivity factor. D is equal to 1 plus beta A, AV. So 1 plus 1 into 4.02. So it would be 5.02. So AVF, it is equal to what? AV upon D. So 4.02 upon 5.02. It would become as 0.8. This is your voltage gain with feedback. This is the first unknown. The first unknown. So solution of the first unknown. Now the second unknown is what? Second unknown is, we have to find out the second unknown is, we have to find out the R0F. So R0F is what? R0 upon D. What is R0 here? Source resistance, because we are considering the feedback across it. I am turn on the chat box. Please give your attendance. So here RS is 1.5 kilo ohm, upon D is what? 5.02. That would become as 0.98 kilo ohm. That is 298, nearly point something would be there ohm. Just calculate through the calculator. This is the one way of finding out the ABF and R naught F. In the assignment, there is a second attached question is there, percentage change. You have to be calculate. That is the mathematical only. Now come to the another way of solving this numerator. So second method is what? Just use the method of the source follower circuit. You have to be first find out the beta, that is your, you can say, what is the beta? V naught upon Vf upon V naught, that is equal to 1. Then Gm, what is the Gm is here? Gm is nothing but same formula, KNID. It would be same, 2.68 milliampere per volt. After that, we know that the formula of voltage gain for source follower, and this would be directly written here as ABS. So what is ABS? It is Gm RS parallel 1 upon Gm. Sorry, this would be, if you remember the formula, it is Gm only. So it would be, what happens? Gm RS upon instead of that, directly write the formula that what you have to be came. There is a not a RD actually. RD is infinite. So actually it was the Gm RS parallel RD. Actually, this is the formula. Now you have to be just write RS upon 1 plus GMI. This would become a formula of source follower output voltage gain of the source follower circuit. That is that thing what with feedback gain. So you have to just put up the value of all these parameters. It would be get the value 4.02 here, and it is 1 plus 4.02, that is again same would become and 0.802. This is the same value as we have already calculated with another method. Okay, now come to the another part, that is R naught. R naught is what? R naught F here. It is RS parallel 1 upon Gm. So first of all, you have to be calculate 1 upon Gm. 1 upon Gm is 1 upon 2.68. So that would become as 0.373 kilo ohm. Okay. Now apply these values here. 1.5 kilo ohm parallel 0.373 kilo ohm. So you would be get the value of R naught F. Then you have to be use this formula, RS into 1 upon Gm, RS plus 1 upon Gm, and put up all these two values. You would be get finally 2.2993 kilo ohm, that is 299.3 ohm. That is the answer. Okay. So this is the way that you have to be solve the problem based on the voltage series feedback. So thank you all of you for attending the lecture today. Still